Hello everyone, I'm Zihe Wang, come from Shanghai University of Finance and Economics, and I'm in the computer science department. And the title of this talk is Geometric Approaches to Auction Design. Well, in a general auction design problem, there is one seller and K goods for sale, and there are a set of buyers. And the buyers knows the exact value for the goods. Well, the seller doesn't know this exact value. He only knows the value distribution. And seller's goal is to design mechanism to maximize the revenue. Well, when there is one good for sale, the Melson has given the optimal auction. Well, when there, what?
Sorry, do the buyers have combinatorial valuations, or is it like additive across goods? When you say they know their value, what does that mean? Oh, there's one good. What was the K? No, but like on the previous slide, there were K goods.
It's just for general problem. I will define the setting in specific problem. And when there is one good, Melson has given the optimal auction. But when there are multiple goods for sale, the optimal auction is very complicated and it is not fully solved. Well, there are several approaches for multiple goods. First is computational approach, and there are many work on approximation on continuous type distributions. And the second approach is programming and optimization-based approach. And people study the exact optimization, but the form of the linear programming solution is not obvious. And the third is the geometric approach, and we use it to study the exact optimization on continuous type distributions. And what is geometric approach? We focus on the shape of the utility surface and how revenue changes with respect to the utility changes. And in this talk, I will introduce two of my works. First is sell two goods, and there is one buyer, and the buyer has independent additive valuations. And the second is selling two goods, and there are NID buyers. And for each buyer, the buyer has negative correlated valuation. Let's see the part one, selling two independent additive goods. Here is the setting. Here is one seller, one buyer, and two goods. And the buyer knows the valuation, V1 and V2. V1 for the first good, V2 for the second. And the seller only knows V1 and V2 are independent random variable with distribution F1 and F2. The buyer has additive utility, and the seller's value for both goods is 0. Here are the notations. We use Qj to denote the allocation probability of good J, and pay is the payment, and the buyer's utility is U. It equals the valuation times the allocation probability and minus the payment. Well, by taxation principle, every mechanism is equivalent to present some set of menu items and let the buyer do the selection. Here is an example. There are 4 menu items, and the first menu item says you pay nothing and get nothing. And the second menu says you get the first good with half probability, and you only pay 0.5. Okay. And in this mechanism, the seller first shows a menu table like this, and then the buyer chooses a menu which maximizes the utility. Then, given such a menu table, how to compute the buyer's utility? You can regard each menu items as a plane, and the basis is V1 and V2. And Q1 of M and Q2 of M is the allocation probability in menu item M. And the pay of M is the payment in menu item M. and the derivative of this plane is the allocation probability, Q1 and Q2. Since the buyer chooses the menu item that maximizes the utility, so the buyer's utility is the supreme of all such planes, and the utility is convex. Here is an example. This is a utility representation. Remember, there are 4 menu items, and they correspond to 4 planes. And the buyer's utility is the supreme of the 4 planes. And you can see this plane, this is the utility plane, utility surface. It is convex. Actually, given the utility function, we can compute the allocation function and the payment function. So instead of designing the allocation rule and the payment rule directly, we design a non-negative and a convex utility function. And here's the results overview. We define the power rate PR sub h of x to be the x times h prime over h. We first show that if the sum of the power rate is less or equal to -3, then the optimal menu is monotone. I will define monotone later. And if the sum of the power rate is larger or equal to -3, then under some conditions, optimal menu is simple. By simple, we mean the number of the menu items is small. Let's see menu monotonicity first. In general, we do not have menu monotonicity. Hart and Rennie gives an example. Under the distribution f alpha, the optimal menu is the following. The buyer has 4 value possibilities. Okay. When the buyer's value is 1, 1, he chooses the menu items 0, 0, 0. Okay. And we say in this menu, the menus are not monotone. It means by monotone, we mean you cannot sort the menu items in a way such that all the allocation probabilities and the payment increases at the same time. Look at these 3 columns. You cannot sort the menu items in a way such that they all increase simultaneously. And also the payment function is not monotone. When the buyer's value is 2, 2, he only pays 1 in this mechanism. And when the buyer's valuation is 1, 2, he pays 2, which is higher. Well, our theorem says if this condition holds, then the optimal menu is monotone. Here is the proof. Look at this figure. A, B, C, D is the buyer's valuation domain. AB stands for V1, and AC stands for V2. And under our condition, the revenue increases as the utilities of buyers increases on A, B, C, D, except on edges AB and AC. And this is the utility surface. So to increase the seller's revenue, we should fix the utilities on AB and AC and increases the utilities on other parts as much as possible. So we draw a vertical line through point A. And for each point on this line, we shoot 2 tangent lines that touches the utilities on AB and on utilities on AC. And these 2 lines forms a plane. And this plane corresponds to a menu item. And the allocation in these menu items are the derivatives of this plane. And the payment in these menu items is the intercept between this cross point and this original point. And when this point goes down, the derivatives of the plane goes higher, and the intercept point goes lower, which means the allocation probability in the menu goes larger, and the payment in the corresponding menu goes larger. And we constructed the utility function as the supreme of all such planes. And we can prove this utility function is convex and it is optimal. So in the corresponding menu representation, the menus can be sorted and such that the allocations and the payment can increase simultaneously. And this completes the proof. And furthermore, we have the theorem about the revenue monotonicity. It says if this condition holds, and G1, G2 first order stochastically dominant F1 and F2, which means G1 and G2 has larger value distribution, then the optimal revenue for G1 and G2 is larger. Okay. Well, Hart and Rennie proves that without this condition, then there is an example of non-monotonicity. Okay.
Going back, I'm not sure I understand the condition. So you defined this PR function to be as given, and it's evaluated at what?
As for every point in the valuation domain.
Oh, if that's true.
For every V1.
Every V1, V2.
Yes.
Okay.
Maybe you can just say, so the fact that the power rates sum to less than -3, what kind of distribution function would satisfy that as a power law? It's like 1 over x to the 1.5, or what would be the density function? What kind of density functions would correspond to that?
The valuation concentrates on the high valuations.
The high value, so it's a fat tail distributions.
Yes. And that's for the menu monotonicity. And now let's move to the simple menu. Well, Hart and Nissen investigate how the menu size of an auction can affect the revenue. And there is a case where the optimal mechanism has infinite menu items. Well, we show that if this condition holds, and under some other conditions, the number of the optimal menu items is small. First, we prove that under our condition, the allocation function in the optimal mechanism looks like this. It contains 4 parts. This means when the buyer valuation in this domain, then he will get nothing. And this means when the buyer's valuation in this part, he will get the second good deterministically. Okay. Then we can express seller's revenue as the functions of utilities on the edges. Then the idea is to fix the utilities on 3 edges and analyze how the revenue changes with respect to the utility changes on one edge. And at last, we can prove that the piecewise linear with 2 or 3 pieces utility function is the best. And here is our theorem. If this condition holds, then the optimal mechanism contains at most 4 menu items. And here's the proof. We prove that for any original utilities on BD, there always exists a 2 piecewise linear utilities that gives weekly higher revenue. And this is the allocation function in the optimal mechanism. it contains 4 possibilities, which correspond to 4 menu items. Here are some other simple menu results. The left one is for the symmetric case, and the right one is for the unit mount case. And that's for the first part. Now we move to the part 2, selling 2 negatively correlated items. In this part, we ask 2 questions. What is the optimal auctions for the following setting? When there are 2 goods and n ID buyers, and for each buyer, V1 plus 2 times V2 equals to 1. Okay. This is an interesting setting, and here are some related works. Armstrong studies when V1 is proportional to V2, shown as this blue-gray. And Levin studies when these 2 valuations has some positive correlations, shown as this green line. And Hakpana and Hartline studies when the distribution in this dark triangle satisfies some log supermodular property. And we study the negative correlation case, shown as this red line. Well, in our setting, we meet some new difficulties. We want to guarantee the Bayesian-incentive compatibility, which means the buyers should be truthful in the Bayesian-Nash equilibrium. Well, we found that the allocation function is not trivially monotone in Bieder's type, and we use Border's theorem to overcome this. And we also want to guarantee the interim individual rationality. And the interim individual rationality means the buyer's interim utility is non-negative. Usually, we want to make sure the lowest of the buyers the lowest utility of the buyers is 0. However, in this setting, the 0 utility is not at the original point. It is in the interval of the valuation domain. And we gave an algorithm to find it. Then after we get the optimal BIC and the interim IR mechanism, we consider whether we can implement it in some other constraint. For example, BIC and IR constraint, or DIC and IR constraint. And this induces the second question. Do these mechanisms share the same optimal revenue? Here are some related works. Kramer and McLean provides an equivalence example, but the buyers has correlated valuations. And Manelli and Vincent proves that the equivalence, but in interim IR setting. And Gershkov provides an example that's inequivalence example, but in a non-standard mechanism. Well, in this talk, we consider the problem in independent private value and IR setting. Well, we give solutions to both questions. We first solve the optimal auction in closed form and provide the first IPV and IR setting where revenue DIC is not equal to revenue BIC, and resolve an open problem by Yao. Here's the setting. There's one seller, 2 items, and n ID buyers. And for each buyer V1 plus A times V2 equals to B. And F is the distribution. And we want to guarantee BIC and the interim IR property. Here are the notations. We use one-dimensional type Pi to denote the buyer's type, and vector T to denote the type profile. And the probability of buyer I gets item J is Qj sub I. And the pay I is the payment, UI is the utility. Well, in Bayesian setting, it is convenient to use the interim representation. And Qj sub I of Ti is the expectation of Q over the other buyer's type. And similarly, we can define the interim payment and the interim utility. And since the buyers are IID, so without loss of generality, we only need to consider the symmetric mechanisms. And these notations, Qg sub I, pay sub I, and U sub I, can get rid of the subscript I. Now, this is the formal problem. We want to maximize the seller's revenue. And in this bracket, this is the buyer's payment. And there are several constraints. The first is the feasibility constraint. It says one item cannot be allocated more than once. And the other three are about the interim IR and the BSE. And you can see only the first constraint involves the full type profile, and the other only involves the interim representation. And by Border theorem says, in the symmetric setting, there exists a feasible mechanism that implements the interim allocation rule if and only if this condition holds. And we use Border theorem to replace the first constraint. And it becomes the following. Now, all the constraints only involve the interim allocation, interim representation. And I will use an example to illustrate how we solve this problem. Consider there are only two IID buyers, and the valuation is uniform, V1 plus V2 equals to 1. We first represent the revenue like this, and then we use the fact that U is non-negative and get the first inequality. And then we use the Merson's ironing technique to get the second inequality. And at last, we use the Border's feasibility constraint to get the third inequality. And the method is very straightforward. We just sequentially apply sequentially use the constraint to get the upper bound. And this upper bound is actually tight. And in the optimal auction, the allocation rule is this. Item 1 is allocated to the buyer with higher earned watch value. And this is the earned watch value. And item 2 is allocated to the other buyer. And this is the interim allocation rule. And this is the interim utility function. You can see the lowest utility point is in the middle. It's not on the boundary. And this is the payment. Well, for general distribution, here is the optimal mechanism. We first determine the zero utility point, and then compare the highest earned watch value with a constant. And there are many sub-cases to consider. Well, after we have this optimal BIC and interim IR mechanism, we consider the second question. Can we implement in other forms? Well, we have the optimal interim IR and the BIC mechanism. Actually, by adjusting the payment rule, we can implement in IR and the BIC mechanism. And Manelli and Vincent says by adjusting allocation rule and the payment rule together, we can implement in IIR and DIC mechanism. So actually, these three mechanisms have the same optimal revenue. Then what about these two directions? Well, our theorem says in the above example, no, the optimal BIC and IR mechanism. In the optimal BIC and IR auction, the optimal revenue is 29/24. Well, no DIC and IR auction achieve the same revenue. That means the other two directions do not work. And this is for the second part. And let's give a summary. Using the geometric approach, we can give the characterization of the optimal auction, and we can also solve the optimal auction in some specific distribution. And we first show that when there are two goods and one buyer, and the buyer has independent additive valuation, if the sum of the power rate is less or equal to -3, the optimal menu is monotone. And if the sum of the power rate is larger or equal to -3, then under some conditions, optimal menu is simple. Well, in the second word, we show that when there are two goods and n IID buyers, and the buyers has negative correlated valuations, then we give the optimal auctions in closed form and provide the first independent private value and IR setting where revenue DIC is not equal to revenue BIC. Thank you.